the session for today. Today's topic is to create a kind of design tool for designers, C# component for designers in order to create a gradational point scattering on top of any given geometry. So it's more like a custom-made Populate geometry node for Grasshopper. And hopefully I could I'll be able to implement that using a simple algorithm with you guys, and hopefully we have some time for you to use that for actual design and to test it out for yourself. All right, and the result looks something like this. You have a bunch of attractor points like these, which you can control which act as some kind of okay, forgot to. I think I have to turn on the audio for a YouTube. I'm also recording in YouTube right now, streaming in YouTube right now. So the topic today is to create a gradational point design tool using attractor points like these to control the force field on top of the geometry to have some kind of gradational pattern like these based on the point position. And you can also use curves by dividing curves into points and use it as a list of points to modify the point cloud like these. All right, so let's get started, shall we? All right. Now, the requirement for today's topic, we only need Rhino 6, basically. If you want to open up the example files that I have uploaded on the GitHub, which you can access from the Meetup webpage or the video description, then you can go to the GitHub page where you can download the README file together with a Grasshopper, three different Grasshopper file, which have some different usage, which shows different usage for this components. The last one, custom populate geometry 3 is using a bit of extended type of component that we're going to create today, and I am not sure if we could make that far. So hopefully I'll be able to finish 1 or 2. Right. So first of all, we have to know the basic algorithm for the normal populate geometry, which is this one that you might have used a lot. So for this one, if you place any geometries as an input to the G with the specified numbers to N, you can populate those points on a geometry with a decent spreading to each other. The points are spread to each other. It's not really randomized, but it is sampled.
Sorry.
Yeah.
The screen isn't shared.
Oops. I thought I had some. All right. Sorry for that. Okay. Should I explain from? Where should I start from? Okay, are you seeing the?
Yes, I can see it.
Right. Okay. Now, where should I start from then? Okay, guess I should start from here again. If you go to the GitHub page, you can have all those information, including the README files together with the 3 Grasshopper files. And the main files that we're going to use, if you want to follow with the file, then you can use this first one, custom populate geometry 1.gh. And the result that we're going to have is something like these, using those yellow points as attractor points to have gradational point scattering on top of a geometry. Also works for a curve as well. If you, well, it actually is a list of points, but if you divide the curve into points, you can also use it with curves as well. Okay. So in order to start creating this custom-made populate geometry node, first we need to actually implement this populate geometry, the default one, which doesn't have any weight option, but gives you a clean sampling on top of a geometry, a picked geometry. So with the number of points, specified points like this. And the algorithm itself is actually explained by David Rutten, I think, right here. It says right here, it's a conditional random insertion algorithm. All the populate components works the same way. A number of random points are generated, and the one that is furthest away from all existing point is picked. And this is done like iteratively to create this kind of clean sampled point cloud on top of geometry. So I have illustrated that algorithm into a sketch where you can check it out inside Grasshopper GitHub. So this is a step that I thought it is for the standard populate geometry algorithm. So first of all, you pick one first random points on top of the geometry, anywhere in the geometry. Then after that, you populate, you create a random points, really random points on top of geometry. And the number of random points could be varied. You can choose that many random points you have, more accurate distancing you could get between the existing point. So after you have the random points, number of random points as a guide, as a guide, from the existing point that you already have on top of the geometry, you calculate the distance for each this yellow random points and find out the furthest point from those lists. Then after that, pick that point to create it as one of the next point which you want to actually plot on the geometry. And you repeat that process. You repeat this process from step 2 to step 4 for a number of times. Specifically, this is the number that you want to plot on the geometry. So if you want to plot 100 points on top of the geometry, you repeat this process 100 times. So that's the basic algorithm for the standard populate geometry without the weight options. So we are going to start to implement this first. Then after that, we're going to add some custom function, custom option for this standard populate geometry in order to create more gradational point distribution based on the attractor points, additional attractor points as an input, right? And if you have any questions during what I'm explaining, you can always stop me to ask, please. because yeah, it's more like implementing a algorithm stuff. So it might be, if some part is unclear, please make it clear for yourself. Right. So the first step is to create a basic setup for the component like this. So we're going to create a empty C# component with some parameters like this. So please go to the GitHub page to have the exact same input types and output. All right. And I'm gonna show you also during the steps. So first of all, I'm going to create a C# script. Then first input that I want to use is the brep, which is going to be the geometry that you want to plot the point on. Right. Then let's set the type hint to brep, this one. And we're also going to add a input called attractors, which will be the point list, which you want to use it for controlling the gravity field of the geometry. So let's use set it as list axis and then type hint as point 3D. Right. Then for a third parameter, we're going to set it to num, which is going to be the number of points. So I'm going to set it as integer, int. And the fourth input will be the iterations, number of iterations. So this is where I have set the number of random points. In this case, the number of yellow random points right here, in order to sample the points. So more points you have, more accurate, more clean sampling you have, less iterations you have, more randomized the point distribution will be. And we can test that later on. So for this one, it is also an integer. Okay. Now, what's the fifth one? Okay. Gotta check my GitHub page. Okay, the fifth one is a attractor radius. So this is attractor radius. Let's set it as _rad. So this is the affection radius for the attractor points. So more distance you have, more affections you can apply for each attractors. And last one will be attractor power. So this is how strong the attracting point is, and that could be either positive or negative. If it's negative, the gravity field goes toward the attractor points, but if it's positive, then the gravity field tries to repel from the attractor point. So that's how you can control. So for those two, I'm gonna set it to double as a type and set it as item axis for both one. Right? Okay. And for initial purpose, for initial setup, we're just going to create a standard populate geometry So we are not going to use attractors or attractor radar attractor powers. We're just going to use brep, num, and iterations for now, right? So for testing, we're going to also create some plane geometry, connect it with the brep for testing. And the size could be any size, but I'm gonna set it to 100 for now, right? And I don't want to show the grid, so I'm gonna hide the grid, right? And for numbers, let's just give some random numbers from 0 to 1,000. Okay. And for iterations, I'm gonna set some random numbers from 0 to 100. Could be more, could be less. We can see that later on. Okay, so let's get to it. If you have any questions until this step, please throw. It's always welcome. If it is okay for you guys, I will continue. Right, now, let's get started. Okay, so the first thing you want to do is to create first random points anywhere on the geometry. So let's do that. But in order to do that, before doing that, we're going to implement some of the namespace and functions that we gonna use repeatedly. So go to the GitHub page again, where it says step 2. So first thing we're going to do is to add this namespace saying Rhino dot collections, which is one of the Rhino Common, which is included in Rhino Common SDK, and by adding this namespace, you can access to some of the Rhino specific collection classes, which is really useful for this component. So we're gonna add this, copy this, and then right here on top of, under the using code scripts, you can paste that right here, like this. Maybe I could increase the font size a bit, maybe a bit more. Okay, so right here, double click this C# component, then add this using Rhino.collections. Then you can access to some of the classes that we're going to use today. And specifically, what we're going to use is this class called point3dList, which is a list class which can contain a list of points, but additionally, it can have really useful functions like find out the closest index from the input point. So that's the reason why I'm going to use this. I mean, you don't really need to use this if you don't want to, but it's much faster to use this with if you want to just find the closest point with the input point. So that's kind of one reason. Okay. Right. Then next step. Okay, step 3. So we're going to add 2 reusable functions that we're going to use a lot in this component. One is a remap function. It is similar to the remap component that we have in Grasshopper, this remap numbers, but we don't have this function in C#, as well as in Rhino Commons, so we have to implement that by ourselves if we want to use it inside the code. So we're gonna copy paste this inside the this Rhino C# component. The place where I find this algorithm is right here from the Stack Overflow. So something like this. So I have just copy pasted and renamed some of the variables. So that's that. And I have also pasted the reference URL to this GitHub. So if you want to check that out, you can also go there. But for now, I'm just going to copy this and paste it to right here. Double click the C# component, and under the custom additional code, you can add your own custom functions besides the run script functions. So let's paste that code right here like this. Now you can use this remap function inside the code. All right, and do the same things for the second function, which is this one. So this is a function to create a random points inside a bounding box of the input geometry. Now for this one, let's write it by ourselves so that we can understand what's going on right here. What's going on this coding. So first of all, the output that we want to get is point3D, right? So we write point3D first, then we're gonna name this function create random point like this, right? And so because we have point3D as a function, so we have to return point3D, some kind of point3D data for this one. And the data that we want to create is the random point inside the bounding box. So I'm gonna set 3 inputs. One is a C# random class that we're going to instantiate inside the run script. And then the other one is a brep, which is the original brep geometry. And then the bounding box of that brep. The reason why I split it with brep and bounding box is that we are going to call this create random points a lot of times inside the for loop later on, and we don't want any like additional like calculations in order to create random points. So if we try to get the bounding box inside this create random points, then that will be too expensive. So we're going to create a bounding box before doing any coding, before doing any like populating, then use it as an input. So that's kind of a reason why I have split it, this one and this one. I mean, you could still get this bounding box from brep inside here, but that's too expensive. Okay, so let's write the code. So what I'm going to do is just create a random x, y, and z coordinate, which is going to be inside the bounding box. Then after that, I'm going to use a function called closest point onto brep so that it will project it on brep. Then as a result, the point will be distributed on top of the geometry randomly. And we're going to test it out by actually seeing how it's being distributed. Okay, so for x, we're going to first make a random value using random class, random dot next double. And the next double creates a random value from 0 to 1 And we want to remap this value from for x to a bounding box minimum x and bounding box maximum x. So that's where we're going to use this remap function that we have just created here. So we're going to remap this random next value, which is from 0 to 1 as a source boundary. And then for the target boundary, that's going to be the bounding box minimum x. This should be n, okay? And target maximum is bounding box dot max dot x. Okay, and let's try to click this play to see if it's any errors, and I do have errors. Okay, the reason why I have had errors because I'm not returning any point 3D yet, so I'm gonna just do this for now. Okay, so this seems to be okay. Any questions so far? Okay, so let's do the same for y and z. Just copy paste the x and rename x to y and z. And as a result, you'll get the point which is inside the bounding box of the geometry. So let's output that first by creating a point using x, y, and z before projecting to the B-rep and see how it looks like. Okay, plus play, check if there's no errors. Okay, so far so good for you guys. Be free to stop the lectures anytime you want to, anytime you have any questions. All right, so if you guys are okay with this, then let's try calling this function for this B-rep inside run script function. So I'm gonna create a simple for loop using this num as a target number. Then call this create random points for a number of points for a number of times. This. And we're going to create a random empty list for points, then add this random points inside this list. Okay, so we need to have 3 inputs right here. First, random class, second, B-rep, and third, bounding box. Now, we don't have a random class and the bounding box class right now, so let's create that first. So first of all, random by new random. If I'm not sure if that's correct. Nope. Okay. Okay, something. Okay, I have to say new list 0.3. Okay, what's next? Okay, so we have random class, and let's also create a bounding box class. And for the bounding box, we're going to create from this B-rep. So that will be easy. We're going to name this bounding box, BB box, and we can get that bounding box from B-rep by accessing to brep.get bounding. Get bounding box. And for a parameter, it asks you to set the Boolean accurate. So if you want to create an accurate bounding box or not, we'll say yes, because we're just going to create one bounding box for one BREP. So that's not that expensive if it's one calculation, right? So now we have necessary information, I think. So the first input, random, will be this one, random. And the second input is BREP, which is this one. So we just name it BREP. And the third one is bounding box that we have created right here. Right, let's test it out. Okay, no errors. Now let's output this point to see how it looks like. Okay, so please check that you have something similar to this, or random point split it out inside on top of the plane like this. And how's it going? Seems okay. All right. Now, this is right now a plane, so the bounding box itself is plane as well. So we want to also test it with the sphere. So connect the sphere, then connect the radius. And you see that right now, the populated or the created random points are actually inside the bounding box of the sphere, but it is actually not on top of the sphere. So next thing we want to do is to project those points on top of the sphere so that we can actually calculate the distance later on. Okay, so to do that, there is a function for BREP called closest point. So we're going to do that right here inside this create random point function. So I'm going to create a new variable called pt and call a BREP dot closest point. So BREP is the original geometry, right? So in this case, this is sphere. And the bounding box is just a box which covered this sphere. And right now the point is actually inside the box, but not on top of the sphere. So in order to project it on the sphere, we're gonna use this closest point function. By creating x, y, z as a point, like this. Then return this newly created pt. Now let's see how it goes with the visuals. Play it. Now all the point has been projected on top of the sphere. Okay, so far so good for you guys. Any questions? Okay. All right. Alrighty. Now that was step 3. Yeah, that was step 3, I think. And now let's get to a step 4. We have done some part of the step 4, I think, already. Now we're gonna add some stuff more. First thing I would like to do is to replace this list point3D with the one that I have shown you before, which is a point3D list class. This one. So let's copy this, or you can just name it right here. We're gonna create a new point3D list and check if there's no errors by pressing this play button. Okay, it simply works just the same as the list of points, but have additional functions on top of the list. So It's pretty convenient for point if you want to use point inside a Rhino command. Now we also want to check if the brep is null or not, because if we disconnect this brep right now, it'll give you errors because it's trying to access the bounding box right here, which is null right now. So we gotta check if the brep is null. If it's null, then we want to skip all those functions. Okay, so we're going to add a condition if brep is not null, then we're going to use those code. If not, we're just going to skip those and just output the empty points. All right, looks good. Okay, how are you guys doing? Good? I'm checking your faces. Okay. Let me know if should I wait or not. Can't tell. Does it work for you guys? Okay, some of you are. Okay, I think I will continue. All right, so now that we have the basic functions to create a random, right now it's just a random points. Next thing what we will going to do is to create a first random point on top of the geometry. So that is, if you go to the GitHub where it shows the algorithm, not this one. Okay. Okay, this is too big. Okay, somewhere around here, this one. This will create a first random points anywhere on top of the geometry. So let's do that. And that will be the step 5 in the GitHub README page, right? Now, so we're going to comment these out first, where we were testing out creating random point on top of the geometry. And in order to know that that the one that we're going to create at this point is the first point, we're going to check if the points list has any existing point or not. So if the number of points inside this point list is equal to 0, which means it is still empty, then we're going to add one initial point. So we're gonna name this random point with the function that we have created here. I'm just gonna copy this. Oops. Copy this one, paste it right here. Okay, and add this into a points list. Okay. And I am going to reconnect this sphere into brep. Okay, so as a result, you should be able to see one initial point somewhere on top of the sphere. Okay. So that's the first point. After you have the first point, we're going to do the next step inside the sketch, which was creating a guide random points besides the existing points right here, which is inside a points list right now. So let's do that. And the number of yellow points as a guide is defined by this iteration number right here. So that means we're going to create another for loop inside right here. For integer t equal to 0, t could be any variable though, and say iterations and create a random guide points. I'm gonna name this nrndpt like this. Okay. And first thing we want to do is to find out the furthest point. So after we have created those yellow points, what we want to do next is to find the furthest point between the points and the yellow points list. So to do that, first thing we want to do is to find out for each random points that we have created right here, which is the yellow one. We want to find out the closest points, closest white points, which is inside here. So currently for this sketch, we have only 1 point. So for every yellow random points, the closest white point is this one. But if we have 2 points distributed, like right here and right here, like this, and if we have another yellow random points again, then first thing we want to do is to find out the closest point for those yellow points for those white points. So let me give a sketch right here. So if we have like 2, oops. Okay, if we have 2 points, which is inside, wow, this is really slow. Okay, this is really slow. Okay, if we have 2 white points and if we have okay, I'm having a slow. Okay, we have 2 white points and then we have like several yellow random points, which is defined by the number of iterations. What we want to do is to find out the pair for each yellow one. We want to first find out the closest white points for this one, this white one, for this one, this one, for this one, this one, for this one, like that. And after creating those pairs, we're going to find out, we're going to calculate the furthest distance from this point to the paired yellow one and from this one with those paired. So let's say for this, for the right white point, the furthest distance is this one, could be like 9. And for the left one, the furthest one is this one, and if it's like 12, and we're going to compare those two, and the furthest value that have as a pair is going to be defined as the furthest point for those two white point. So that's how we are going to find out the furthest point from those yellow random points using the multiple existing white points. So keep that in mind. We're going to implement that using code. So first of all, we are going to create, we're going to find a closest white point for each random point that we have created right here. So this is the yellow points, right? Now to do that, there's an easy function in order to find out the closest point, which is stored inside this point3D list. So that is, and for using that function, you can find out the closest point index of that item inside the list. So I'm gonna name this an index, and because we're going to check those white point list and use the function called closest index with an input point 3D variable values, which is this one that we have just created. Okay. Oops, like this. Now that we have found out the closest index for the random points inside the point, although we only have one initial point right now for the first loop, so it's just gonna be one index, I guess, 0. Next thing we want to do is to get the actual point position using this index. So that is points and index. Wait. Okay. Right. And next thing, we want to calculate the distance between this picked position and the random position to actually calculate the distance. So let's name this ndist and npos dot distance to and rndpt. Yes. Okay. So this is the closest distance between the random points and one of the white points. All right. So after this, we want to check if this distance that we have calculated right here is going to be the furthest point distance or not. So in order to do that, we have to have a parameter outside the for loop, or not the parameter, the variable that we're going to store the furthest distance, maybe starting with a value of negative values, because the distance will always going to be positive. So let's create a variable like f distance initialized with -1, -1. And if the distance between 2 points, which is the distance between the yellow random scattered points and already existing white points, is greater than the furthest distance, the current furthest distance, which is currently -1, then replace this furthest distance with the one that we have calculated right here. And by doing it iteratively inside this loop, we can update this furthest distance for each random points, and we are able to find the actual furthest point by doing this. And also we want to retrieve the furthest point position as well. So we're going to create a variable called point3d fpos initialize with empty point position 000 position. Then also update this f position when the nearest distance is higher than the furthest distance right here. So the update that we're going to use is this random position that we have created right here. So this is the yellow position. So this is going to be the furthest random yellow point position. So after leaving the loop, you'll be able to get those f position as the furthest point position. So now you can add this inside the points as an additional point. So which is same as for this step 4 in the sketch. You have found down the furthest point, the yellow point, and you have just added to the point list. And continue doing it iteratively by filling the space with the specified number of points. And that is already written by right here. So after adding the points right here, we are continuously adding the points until it fills up the plane with this number. Okay, let's check that out. And okay, errors, of course, where that NR, okay, spell mistake, typos, 81, NR and DPT. Okay, now I am seeing I'm seeing the cleanly distributed point cloud on top of the geometry. Okay, so far so good for you guys. So this is how you can implement the standard populate geometry, which you don't really need to if you just want to have the clean like sampling like these, you can just use this one. But I think the actual algorithm inside here is something like this, but maybe more efficient right here because it's a bit more faster than this one. Okay, any questions so far? The benefit of writing this algorithm by yourself is that you can add your custom options. So that's a great benefit, I think. All right. So far, so good. That is...
excuse me.
Yes.
Let me ask you something. What type iterate? I have error. The type difference.
Really? This is the iterations is integers right now.
Yes, integer.
Number is also integers. Brep is brep. And what else? Well, that's all we're using right now.
Yeah, combo.
I think I can. Okay, let me open up, scale up my window to see your display. Okay.
This error is convert operator to an int and object operand. It can not be applied. But
are you having?
But it seems to be just my environment. So
did you? Can you check these iterations like by right-clicking it?
yes, yes.
and then go to the type and then set the integers.
Ah, okay.
Okay, right.
Yes, thank you.
Okie dokie. Anybody has any questions so far? It's okay for you all. So after we have this kind of implementation, we're going to add weight options, attractor options, so that we can control those point sampling, using a kind of a gravity force to create something like a gradational point cloud. Right, and that is not that hard actually. So I'm going to close this a bit and create an input for attractors first. Okay, so we have 3 input for attractor information. So one is the list of points, one is the radius of the attractors, and the one is the power of the attractors. And for the list of attractors, okay, let's just use this sphere as a test geometry, and I'm going to use this Populate geometry as a source of attractors. So I'm gonna set it to something like low numbers like 3. And currently I have 3 random point on top of this sphere, and I'm gonna use this as a attractor points in order to control the Populate geometry, custom Populate geometries point cloud, and put it into attractors. This. Now for the radius, it is a double value, which in this case, the radius of this sphere is 100, so it could be something between 100 to 200, maybe 200, and I'm gonna set the maximum to 200 and set it as real numbers. This, and for the power, it could be either negative or positive, so I'm gonna create a sliders which goes from -1 to +1, like this. So -1 to +1, +1. Okay, and if the value is 0, I would like to have the scatter point something like this, even if you have attractor points. If it gets to positive, then I want to use those attractors to have the repel forces. If it's negative, I want to set those attractors as a gravity forces. Okay, or maybe vice versa, I'm not sure. Okay, so after I have put those values right here, let's go back to the code and then write some additional ones in order to implement this weight option. Okay. Now the place where we want to use those attractors is, now first of all, let me explain the algorithm for the attractors. Go back to the GitHub page and to the right side of the sketch. Okay, let me go back to right here. Okay, so the left side was the standard algorithm for Populate geometry, and the right one is the weighted Populate algorithm, where you want to use attractors to modify those point distribution. So the things that I'm doing here is to use those. So in this case, the black point is the attractor points in this sketch. And I'm going to use those black points in order to modify the position of each yellow one by the distance between the black one and the closest white point. And do the same for the other attractors as well. And use that as a weight value. Oh, sorry, that was a mistake. First thing you need to do is to find out the closest attractors for each point. So for this white point, the closest attractor is this one. So this will be the the force that we're going to use for this attractors, for this white point. And using those attractors, I'm going to modify those yellow points by making those point closer to the black one, or further going to the other direction, maybe this way if it's positive. If it's negative, going closer. If it's positive, it's going further. Then after that, the new position will be made for those yellow random points. And then from that, we're going to calculate the distance from the white point and the yellow point as we did last time for the standard populate geometry algorithm. Then use that distance to find out the furthest point. So what we're doing here is to modify this distance with distance value by this attractor point. By using this, using those attractor points to as a force to change the actual random point position using those vectors, vector field. The actual distance after we have modified the point, yellow point position is going to be different from the standard one, which is right here. So before, the furthest point was right here, but after modifying the yellow point position, then the furthest point became right here, and the original position, which was for this point, was at right here, because this point was moved from here to here. And we're going to use the original point position when we want to add it as a new point. We're going to use this just to calculate the distance, the furthest distance. And after we have calculated the distance, we're just going to use the original random yellow point position as a point to add inside a white point list. And as a result, you'll get something like this, more like a weighted gradational point distribution modified by these attractors. Got it? It might be a bit hard to imagine first time, but let's try to implement that using script and see how it really works. Okay, let me bring this back upward. Also this one upward. Right. So that is going to be a step 6 in a GitHub. And the place where we're going to add attractor functions is just underneath this distance value. right here. So after we have created the random points, which is the yellow points, and we have found out the closest index for each white point to the yellow point, and we also have got the point position, white point position, closest white point position from that yellow one. And the next thing we want to do is to calculate the weighted distance. So we're not going to use this one. Instead, we're going to calculate a new distance value based on the attractor positions. So first of all, we're going to find out the closest attractor point, which is from here to this random points first. Okay, so I'm gonna name this an attract ID. I'm gonna use this the same function, closest point, closest index right here. So in order to do that, we need to use a point 3D list. And right now, attractors is not point 3D list, but it's a list of point 3D like this. So we would like to convert this one into this list, this class. And that is not that hard to do. We just need to say var attracts new point 3D list attractors. So this is how you can convert the list of point 3D into a point 3D list class like this. Now, after converting this, you can access to a really convenient function called closest index. So attracts dot closest index with a random point that you have created right here, right? Okay, now next thing, we would like to get the point position of that attractors. So an attract position is attracts ID, which I have get it here. Right. And let's also get the, oh well, before going to the detail, is there any questions from you guys? Is there okay? Is everything okay? I'd like to know if there's any problem. It's okay. I'll just continue. Okay. So next thing I would like to do is to actually calculate the distance using those attractor position. So first of all, I'm going to calculate the distance between this attractor position to this random point position right here. Okay, so I can do that by an attract position multiplied by, dot distance to random point this. Okay, now this is going to be the linear distance between the point between the attractor points and the random points. So, and I am going to name this as, how do I name this? And attract distance. Now, this actually is what I have calculated right here, the distance between the attractive position and the random point position is the weight itself. But right now, I haven't modified the weight distance using any functions like power functions. So this doesn't really give you any like how do I say, modifications to the original point scattering like this, I think. So in order to use this as a attractors, you have to have some kind of functions like math power, or maybe a sine wave or logarithm or something like that, in order to change those value depending on the size of this value. Now the power is really convenient to use, so I'm going to use power for these examples. And in order to use the power, you need to have the second input, and that is going to be the value that I have set it as a parameter right here, attractor pow. And let's copy this and paste it right here. Okay, and we're also going to we also want to limit the affectant distance by using this attractor radius. So we're going to copy this as well and set the limitation how much it can affect, how much this weight can be affected. And that can be placed somewhere around here for this attractor distance. So for attractor, the distance between the attractor position and the random position, we can put another function called math.minimum and just get the minimum distance value between the value right here and the attractor distance, attractor radius right here. Okay, right. All right. Now we can also remap this into 0 to 1, I guess, but let's see if this itself works. I think this itself also works. So in order to use this after creating the weight value, which is right now called inner attract distance, we just need to multiply this distance value from the nearest point position for the yellow, for each yellow one, which is this one, multiply by this and attract distance to use it as a weight value, right? And that's kind of all you need to do if you play it and see how it's going to look like. And yeah, I think I'm seeing some changes right here. Let's close this. Okay, before closing this, you guys have got the coding like I did right here. Let me know if you have any questions. I'm not sure if anybody is using a chat to throw a question. I cannot see a chat right now. I'm not sure. Anybody having any questions? If not, okay, I will continue. Okay, so if you are okay with it, you can press OK and see how it looks like. Now I have set the power value to -7.9 at this point. If I set it to 0, it should be a standard scattering mode, which doesn't have any modification. 0 means the power of 0 means this one become 1. So this distance multiplied by 1 is like it's no change. Nothing changes with compared to the default one. So there's gonna be no changes, but if it's going to be either negative or positive value, then the distance will, you should have some kind of weighted value by modifying the distance between the random value, random point, and the attracting point, which causes a deformation, which causes the deformation for the distance calculation, distance function, which creates this kind of gradational distribution. If you set it to negative, the points will try to come close to the attractor points. If it's positive, it's trying to go farther away from the attractor points. It's a bit hard to see with this. Maybe I should make the sphere solid color. Preview. And where is the attractors? So these are the attractor position. And if I make it positive, the point close to the attractor becomes less compared to the point that is far away from those attractors. If you make it negative, you have opposite conditions like this. And this works for any kind of geometry, like plane, of course. Plane is more easy to understand, I guess. So these are the attractor points, and even if you change the attractor point position, it still works. And by changing those attractor value from negative to positive, you can change the distribution, the gradation, and you can also set the maximum affecting radius for these attractors. If you make it low, then a very small amount of points, which is close to those attractors, will be affected, right? So that is the basic, well, I am not sure if it's basic, but that's how you can implement this kind of custom populate geometry with the weight option in order to create this kind of scattered controlled point distribution on top of any geometry, right? And if you go back to the GitHub, that was for file 1. That was right here, custom populate geometry 1, and custom populate geometry 2 is just an example how to use this, using this component as a design tool. So I'm not going to get deep into that. You can just follow that file and see how what's doing that. So I'm just let's just open this. Let me just explain first. So I'm just creating a half sphere, oval sphere like this, and then creating a scattered point on top of this sphere. and using the edge, the naked edge of this sphere, the naked edge of this half sphere as a attractor point position. So more closer to the edge, more points you have. Farther from the edge, you have less points, and use those points to create a 3D Voronoi to create some this kind of structures. So that's what I'm doing in file 2. And I'm using Weaververt for this example. So if you haven't installed that one, you need to install that in order to actually see that. And I am seeing some errors here. Okay, what seems to be the problem? Okay, so at some pattern, sometimes this simple mesh doesn't work. So let me change the parameters a bit, like setting it to. Okay, now I got something. It's a bit too long to connect those components, but it's pretty doing really simple things. Having those components that we have made here on top of this half sphere and using this edge curve right here, naked edge of this sphere, which is the bottom curve. I have divided this curve into a list of points like this, so that I can use it as a attractor points, and put it right here directly to the attractors, and this sphere as a B-rep, then control some of the parameters right here in order to control some distribution. If I make it more negative, then you have more points on the edge. If you make it positive, you have less point on the edge, but you have more points on top of the sphere, something like that. Right? And after that, it's just a simple design method, just using those points to create a 3D Voronoi and create some frames, extrude it, make it 3D, voila, like this. Well, yeah, it's not that interesting, but it's one way to use. And I would like to see how you would use this like custom tool for your design purpose. So if you got any design using this method, using this component, I would like to see. Yeah, I would like you to let me know what kind of design you could think of from this. And although there is one limitation with this component, if maybe some people might have noticed it, is that right now this component only accepts one type of attractor radius and one type of attractor powers. So if you want to use multiple attractor points for each attractor points, this doesn't work. This doesn't really work. It just makes a double point cloud. So this one and this one is treated differently. Makes individual, use it as individual powers. So in order to use multiple attractor powers and multiple attractor radiuses, there is a bit of update that you need to do. And we could do that during these sessions, or if you guys are tired, we can stop it. You can check that code from the custom Populate Geometry 3. This one is actually a newly updated component which accepts multiple attractor radiuses and attractor powers. So as a result, let me just show you demo how it looks like. So say you have, right now you have 3 attractor points for this one, 1, 2, and 3. And as you can see, 1, 2 of the points are used as a cohesion force, and other one, the last one, is used as a separation force. And that is controlled by this value, 3 different values. So if I change those values, you can customly change those attractors one by one using different values. And same for the attractor radiuses as well. You can control the attracting affection radius for each point. And to do that, you need to do some updates for the last code that we have wrote. So I want to ask you if you want to follow that, if you want an explanation for that, I can do that. If not, I can finish it right here and have your own design using this code. Okay, how's that? Let me know how, your opinions. If I don't get any opinions, I'll just finish it right here. If you're good at reading code, you can just double click right here and see how it looks like this. By looking at it, I think you'll get it. You'll get what is going on right here, what is added to the last code. Okay, so can I have your opinions, please? Everything good? Okay, I guess we could finish at this point. Thank you very much. And I hope I hope I showed something new for you guys. Okay. 終わりです。しゅうさんの声が聞こえる。
Thank you very much, Horikawa-san.